Hello, I'm Sean Datta. I'm a PhD student at Stanford, and I'm going to share our work on exponential improvements to the hardness of random circuits, and in particular boson sampling. This is joint work with my advisor Adam Bouland, Bill Fefferman, and Felipe Hernandez. This is a talk about sampling from random circuits, for which there's a very beautiful theory that's flourished in the last 15 years. I want to share 3 perspectives on why this is so fascinating. The first is we've now seen many experiments that all solve variants of random circuit sampling, and it behooves us to ask, what is the power of these experiments? How compelling are they as potential violations of the extended Church-Turing thesis? The second reason is more fundamental. Is quantum computing more powerful than classical? Is BQP different than BPP? This is the premise of our entire enterprise, that quantum computation goes beyond classical. We have excellent oracular or black box evidence separating classical and quantum computation. What about white box evidence? Our dream theorem would be to separate BQP from BPP, but it's utterly beyond our current techniques to prove it. For now, it is only a dream. What about the next best thing? Showing that BPP containing BQP would collapse the polynomial hierarchy. Also well beyond our current technology. The miracle is this. If we move from decision problems to sampling problems, we can actually prove this via sampling from random circuits. The first results are now 21 years old, so what's the problem? The problem is that these results are very brittle in the sense that they're worst case and exact. They tolerate no imprecision or hardly any imprecision at all. For this to be more than just an artifact, we need to show that these results are robust, that they are robust to imprecision, and that they extend to the average case. And I'm here to tell you, all these years later, this remains an unfulfilled dream. In this talk, I'm going to convince you how much closer we are to now realizing this dream at last. So what is my take-home message for you? If you want to separate BQP from BPP for some computational problem, then this is your best bet. Our reasons to care so far are physics experiments and complexity theory. The third reason is cryptography. Recent work has showed how so-called microcrypt primitives exist if sampling from random circuits is hard classically. So we'd like to remove the need to base these cryptographic primitives on unproven conjectures. That's why sampling from random circuits is worthwhile to study. Now let's all get on the same page as to what precisely these sampling problems are. They have 3 steps. First, you initialize some fiducial starting state. In the case of RCS, that's the all zeros string. Next, you evolve by a circuit drawn at random from some circuit family. For RCS, that's a brickwork circuit with randomly chosen gates. For boson sampling, it's a randomly chosen linear optical circuit. And finally, you measure to generate a sample from the output distribution. For RCS, that simply means measure in the computational basis. As an example, I've illustrated these 3 steps for boson sampling. All we need to know about boson sampling for the purposes of this talk is that its output probabilities are proportional to permanence of IID Gaussian matrices squared. So each matrix entry is drawn IID from the standard normal. Remember, our motivating question is, how hard is it to simulate random circuits? I alluded to unproven conjectures, and now we'll see what those unproven conjectures are. Prior work showed that classical computers cannot sample from random circuits if it is sharply hard to estimate their output probabilities to within some additive error delta. Of course, that delta depends on which ensemble of random circuits you use. For random circuit sampling, delta goes like 2 to the minus n, the number of qubits, and for boson sampling, e to the minus n log n minus order log n, where n is the number of bosons. These quantities are essentially 1 over the Hilbert space dimension. In the case of boson sampling, the conjecture that it is sharply hard to this delta has a name. It's appropriately called the permanent of Gaussian's conjecture, recalling from the previous slide that the amplitudes are proportional to Gaussian permanence. And the central open problem is to prove one of these conjectures for any random sampling task. All are open. What's the status of proving these conjectures? We want to show it's hard to estimate output probabilities to plus minus delta, but so far we've only proven it's hard to within some delta prime that's much less than delta. This additive error delta is often called robustness, so this gap between delta prime and delta is appropriately called the robustness gap. and our goal should be to close the robustness gap. So what's the status? I've tabulated this for boson sampling, and there's an analogous story for random circuit sampling. Let me highlight one thing in particular. Although the previous best robustness looks sort of close to the goal given to us by the permanent of Gaussian's conjecture, it's still exponentially far away in relative terms. In this work, we improved the robustness so that it matches to the first two orders what's needed to prove the PGC. In the exponent minus n log n minus n, minus order n to the epsilon for any positive constant epsilon. What's needed now to close this robustness gap is to improve this third term to order log n. Why has progress been so difficult? Well, there are classical algorithms that have solved related tasks, but maybe the deeper reason is that there are many known proof barriers, meaning that prior proof techniques could not possibly prove hardness of sampling. Some are specific to boson sampling, some specific to RCS, some applicable to all species of sampling experiments. I'll highlight some of them in due time, but what I want to highlight for now is that in this work we overcome all known proof barriers. In the absence of a resolution to the PGC, there's a disconnect between existing hardness results, including the first theorem I shared, and the computational problem that the experiments actually solve, which is a sampling problem. Our second major result is to show that we can lift our new results on estimating output probabilities to prove a hardness of average case sampling theorem. So our first major theorem is about the hardness of estimating output probabilities, and our second result is about proving hardness of sampling. We prove that there is no classical sampler that fails for no more than 2 to the minus cube root n fraction of instances of size n, i.e. sub-exponential scaling in n. Now let me say all anyone knew how to prove before this was that there is no trivial sampler that succeeds on 1 minus 2 to the minus n fraction of instances. We want to show 1 over poly, so more remains to be done, but this is the first non-trivial hardness of average case sampling result. Let's begin to sketch the proof. Let's begin with the standard worst to average case reduction, which harkens back to the proof of Lipton from 1991, which was adapted by Aronson and Arkhipov. This is really a sublime proof from the book. Let's consider the permanent of R of t, a convex combination of any random matrix R, in this case IID Gaussian, and an arbitrary, say, binary matrix W. This object has 3 desirable properties. Firstly, it's a polynomial in T of degree n. This is just by direct inspection of the definition of the permanent. And by the way, here we're talking about the permanent, but for RCS, the degree is like the number of gates in the circuit. Secondly, the distribution of R of t is very close to that of R for small t. This follows from a straightforward calculation. And thirdly, R of 1 is W. This inspires the following reduction, whereby one uses the ability to compute the permanent of R to compute the permanent of W. The key idea is polynomial extrapolation. We consider permanent of R of t for small values of t, where by assumption we can compute its values, and we extrapolate a polynomial through those points to t equals 1, where we have permanent of W. Thus we can compute permanent of W if we can compute permanent of R. Hence, worst to average case reduction, the average case is as hard as in the worst case. What's the problem with this reduction? The problem is that polynomial extrapolation is terribly ill-conditioned, in a sense that we can make quantitative using what's known as the Remez inequality. It tells us that to estimate a degree d polynomial to within some error delta on an interval, the blow-up at t equals 1 goes like delta times the extrapolation distance to the power of the polynomial, d. From the Remez inequality, we get a very simple prescription, and the moral is this. To improve robustness, we need to decrease the extrapolation distance 1 over delta, or decrease the polynomial degree d. Each technique we develop will have this purpose, to decrease one or both of these quantities. And in our work, we introduce a suite of new tools to do just that, to decrease the extrapolation distance and decrease the polynomial degree. Coefficient extraction, dilution, the square trick, magnification, and 2 so-called rare events lemmas. These tools get around all the proof barriers and exponentially improve our evidence for the average case hardness of random circuits, both for the robustness of estimating output probabilities and for sampling. In this talk, I'll focus on just a few. Our first idea to decrease the degree we call dilution. The basic idea is to shrink the size of the worst case instance relative to the size of the random instance. Previous reductions used a worst case circuit, in particular a Fourier sampling circuit, acting on all n qubits. So here's a simple idea. Let's consider instead the circuit on the right, acting on n qubits with a bipartition into A and B. But now, only circuit WA is a worst case circuit acting on n to the epsilon qubits, any constant epsilon greater than 0. And R of B is just a random but fixed circuit on the remaining qubits. So we've just shrunk our worst case circuit relative to n. And on the interface between A and B, we have identity gates. So the first immediate observation is that by construction, the output probability for this circuit factorizes. For example, the probability to measure the all-zero string is simply a product of the probability from WA and from R of B. And here's the key observation. Since WA is a worst-case circuit, the probability to measure zeros on the A qubits is sharply hard to estimate multiplicatively. This suggests the following strategy. Since I just argued that P0 of WA is sharply hard, what we now want to do is to show how we can estimate it given the ability to estimate P0 of a random circuit. That's what it would mean to give a worst to average case reduction. And since by construction the probabilities factorize, P0 of WA is P0 from the overall circuit divided by P0 of R of B. So what we need are multiplicative estimates to the numerator and the denominator. Well, the denominator we get for free. Since R of B is a random circuit, by assumption we can estimate P0 of R of B. What about the numerator? Well, Wn is a worst case circuit, so we can simply implement the previous worst to average case reduction, but here we only extrapolate over the gates in WA. That is to say, all the circuits in our extrapolation path will share R of B on the B qubits. So then the degree of the polynomial will shrink to the size of the support on WA, which is n to the epsilon. And remember, our error blowup goes like extrapolation distance to the polynomial degree, both of which we've decreased. So, after some arithmetic, we obtain robustness that is very nearly what we would need to reach the target of 2 to the minus n. And recall that for RCS, 2 to the minus n would suffice to show no classical sampler. A feature of this argument is that it circumvents the depth barrier. So what is the depth barrier? Well, we expect random circuit sampling to have a phase transition in depth from easy to hard. And intuitively, the reason is entanglement. A shallow circuit cannot entangle qubits as much as a deep circuit can. And indeed, there have been efficient classical algorithms, most notably from Knapp et al., that have been able to exploit this low entanglement using tensor network methods to sample from very shallow random circuits. Yet, prior hardness results were depth insensitive, whereas evidently from these efficient classical algorithms, hardness of sampling can only kick in at sufficiently large depth. Our argument requires anti-concentration of random circuits. Why? Recall we estimated a quantity that was numerator over denominator, and the denominator was the output probability of a random circuit. This needs to be bounded away from 0 or the quotient blows up. That's exactly what anti-concentration gives us, that this happens with sufficiently small probability. And the depth dependence is exactly what you would expect it to be, which is at log depth. That's where the action happens for random circuits. Now let's see what happens when we try to implement the same strategy for the permanent. Remember, the idea of dilution is to shrink the worst case instance W prime to be polynomially smaller than the size n of the random instance. And again, by padding, the permanent of W prime is still sharply hard. So our worst case instance W dilute looks like the matrix on the right. And so we'd like to implement the game plan that worked so well for random circuit sampling, which is to extrapolate 1 minus TR plus TW dilute to t equals 1. When you try this, there's good news and bad news. Remember the moral. To increase the robustness, we need to decrease polynomial degree or extrapolation distance. The good news is that this does both. But now the bad news. If W dilute has small support, as drawn here, then its permanent is simply 0. This follows immediately from the definition of the permanent. So polynomial extrapolation does not encode information about the Sharp-B-hard quantity, the Sharp-B-hard permanent of W prime. What are we going to do about this? Let's consider instead R of t equals R plus TW dilute. Let's simply drop the 1 minus t. Why would we do such a thing? The permanent at t equals 1 is just the permanent of R plus W. That's not very interesting, but permanent of R of t does encode the Sharp-B-hard permanent of W prime, and it does so not in its value at t equals 1, but rather in its leading order coefficient. So if you write out the permanent of R of t in powers of t, you will see that it is a polynomial in t of degree n to the epsilon, and its leading coefficient is permanent of W prime times permanent of the complementary minor R of d. So now what's the idea? We want to extract an estimate of permanent of W prime, but we only have access to it multiplied by the permanent of R of d. But remember, by assumption, we have an average case algorithm to estimate random permanents. So now we can simply make a recursive call to that algorithm on the smaller instance R of d. So we can extract the Sharp-B-hard quantity out of the leading coefficient of permanent of R of t, given the ability to estimate random permanents. A nice feature of our proof is that it circumvents the JSV barrier. So what is the JSV barrier? It refers to a celebrated paper of Jerem Sinclair and Vagoda 20 years ago that gave a polytime randomized classical algorithm to approximate the permanent of a non-negative matrix to small relative error. So if your objective is to approximate the permanent to within small relative error, then non-negative matrices are easy, and mixed sign matrices, meaning positive and negative entries, are hard. Yet prior proof techniques were insensitive to the difference between non-negative and mixed sign matrices. By contrast, our proof is sensitive to mixed signs. Why is that? Well, our reduction obtains the worst case permanent to small relative error, and for this to be hard, the matrix needs to have both positive and negative entries. So I've now sketched two of several techniques we developed to increase the robustness to which we can show it's hard to estimate output probabilities. And we can lift these results to prove a hardness of sampling theorem, but we need one last technique. Remember the moral that framed all our techniques. To improve robustness, we need to decrease the polynomial degree or decrease the extrapolation distance. And the suite of techniques we introduced to increase the robustness of estimating output probabilities gets us to within striking distance of our goal. In particular, I claim that if we could estimate the permanent of R of t at t equals 1 over root n rather than 1 over n, then we would show hardness of sampling. That won't be obvious, but I make the claim that that's what's needed after deploying our other techniques. So what's the problem? The problem is that R of t for such large t is very far from IID Gaussian and total variation distance. So there's no guarantee that our average case algorithm will work so far out of distribution. But what we prove is that we can estimate perm of R of t so far out of distribution if our average case algorithm works with sufficiently high probability. This is what allows us to prove a hardness of sampling theorem for a sampler that succeeds with this very high probability. So now we're going to set our sights exclusively on this goal of decreasing the extrapolation distance. And the key idea is this. Look at these two shifted Gaussians, which are the distributions for a single matrix entry of R and R plus T shift W. The key observation is that R plus TW is also Gaussian, just with shifted mean T. So in the figure we have Gaussian G, shifted Gaussian G shift, and we color successful events blue and failure events orange. Our tail events in orange are that the algorithm fails. Remember our motivation. We want to estimate the permanent on R plus T shift W for a large T shift. And the figure illustrates that events deep in the tail of one Gaussian are still tail events for a shifted Gaussian with some much larger failure probability. In particular, we prove that a tail event with probability e to the minus t squared under g has probability 1 over poly under g shift. That means that if our algorithm works with very high probability, then we can reliably estimate the permanent even for these far out of distribution values of t. We show how to combine this with a very technical second rare events lemma that collectively implies that there is no classical sampler that fails with probability 2 to the minus cube root n for input size n. Just as a reminder, that's of course weaker than what we'd like to prove, which is 1 over poly, yet it's also an exponential improvement over the trivial scaling. A final caveat. Because we estimate R of t so far out of distribution, we need those far out permanents to anti-concentrate, just like we did in our dilution proof. That doesn't immediately follow from standard permanent anti-concentration, but in the paper we show that in some sense it interpolates between standard permanent anti-concentration, which holds at t equals 0, and for large t, it's also proved outright. So we merely conjecture that it's true in between the two extremes. I have just one open problem to pose to you. Can we at last prove the permanent of Gaussian's conjecture? And with that, I thank you for listening.